Okay, let me start the course. So if you recall, in the previous lecture, we talked about FDA, Fisher discriminant analysis. Fisher discriminant analysis is a technique for feature extraction, dimensionality reduction. And we learned that when we have two classes, basically we project everything on a line, on one border, on one vector. So if I call this vector W, basically all x's in Fisher discriminant analysis, all x's would be transformed to W transpose X. Clearly, the mean of each class will be transformed by the same projection. So for the first class, for the second class, and then covariance of the class will be transformed quadratically. So in FDA, we wanted to collapse each class separately and then take these two classes as far apart as possible to make a good distinction between two classes in the projected space. So we had two goals. One goal was to collapse each class. Basically, we wanted W transpose sigma W plus W transpose sigma 1 W to be a small. And we realized that we can write it this way. And we call this within class covariance. That was the first goal. And another goal was to take classes far apart. And it turned out that we can write it as W transpose mu0 minus mu1 times mu0 minus mu1 transpose W. And we call this SB, between class covariance. And we wanted to maximize this and minimize this. So we had an objective function of this form. And we realized that we can write it as a constraint optimization problem, put a constraint on denominator, and then we can write a Lagrangian for that, and Lagrangian has this form. Lagrangian function of primal variable and dual variable has this form. And then when we take derivative of L with respect to primal variable and set it to 0, the derivative is SBW minus lambda SWW, and which means that SBW is equal to lambda SWW. And you can take the inverse of SW multiplied to both sides. Then you have SW inverse SB. W is equal to lambda W. So clearly, this is an eigenvector problem. And W is eigenvector of SW SB, SW inverse SB. I also mentioned that SB, as you can see, is rank 1 matrix because it's a multiplication of two vectors. So it's rank 1, so the total rank of SW inverse SB would be 1. So this is rank 1, so there is only one eigenvalue and one eigenvector, one non-zero. So there is only one eigenvector, means we have only one direction for projection. So when we have two classes, we can project everything on one vector. So it's in contrast with PCA that we were able to reduce the dimensionality in any dimension that we want less than the original dimensionality. We can do this here. You know, it depends on the number of classes. For two-class problem, we can project it only on one direction. For k-class problem, we can project it in k-1 direction in general. Okay, so that's the general solution. But this general solution, I can simplify the solution for the case of two classes. You know, SW inverse, SB is the multiplication of these two vectors. W equal to lambda W. And we need to solve for W. Okay? This is a D by D matrix, right? What's the dimensionality of mu now? It's the mean of data points, and data points are in D-dimensional space. Sorry? It's D by 1, okay? So this is D by 1. What about this one? 1 by D. What about W? It is? Sorry? Don't forget, you know, that this was D by 1. And W transpose X was just a scalar, right? We project everything. So what's the dimensionality of W transpose? 1 by D, right? So W is D by 1. And this is a scalar, and this is also D by 1. Okay. So I have, you know, usually this SB is D by 1, 1 by D, which makes a D by D matrix times another D by D matrix, and then D by 1 vector. The left-hand side would be D by 1, and right-hand side would be D by 1. So, but if I write what the SB is, I can look at this part. You know, I have 1 by D vector times a D by 1 vector. What it is, I mean, a 1 by D vector times a D by 1 vector would be a scalar, right? So here I have a scalar. Let's call this a scalar C. It's a number, okay? So if I call this a scalar C, then I have SW inverse times mu null minus mu 1. Then I have a scalar, which I don't know what this scalar is, equal to lambda, which is another scalar, times W. Okay. Don't forget that when we find W, we don't care about the length of W, right? We just care about the direction of W. I want to know on which direction should I project the data. It doesn't matter what the length of W is. So basically, it doesn't matter what the lambda is, what the C is, you know, because the role of this lambda as C is just to change the length of W, right? I can say that SW inverse mu 0 minus mu 1 is equal to lambda over CW. So this has to do with the length of W. It's just a scalar. We change the length of W. I don't care about it. You know, it doesn't matter. I can say that W, anyway, is proportional to SW inverse mu 0 minus mu 1. Okay? That's the only thing that I care about. I don't care the length. So I just need to know the direction, and this gives me the direction. So for two-class problem, it's easy to find Fisher's discriminant analysis. Just find SW, which is summation of the covariance of two classes. It could be weighted sum based on the number of points in each class. Say, for example, you have 50 points here, but 100 here. So 50 times this plus 100 times this divided by 150. It could be weighted. But anyway, it's sum or weighted sum of covariance of two classes. Take the inverse. And you have the mean of two classes in the original space. Multiply. It gives you the direction of the vector. So this is d by d, and this is d by 1. So this is going to be d by 1. So d by 1 vector, which is the direction of FDA. So we can basically project everything in this direction, and they are going to be separated. These two classes are going to be separate. Any question here? Okay. So what if I have more than two classes? So in general, we have K class. So FDA for K classes, I had, if you remember, I had X, and in two class, I projected X using one vector. When I have more than two class, basically I want to make separation between all of these classes pairwise, right? So I'm going to use matrix W, not just vector W. In this case, this matrix is basically, some vectors that you can prove that the maximum number of them is k minus 1. So there's k minus 1 different directions for projections. So you can basically transform data, not just project data. You can transform data using this linear transformation to a new space. And the mu will be transformed accordingly for both classes. And sigma will be transformed quadratically. Okay, so if I get back to the steps that I had before, I wanted to maximize the, I wanted to minimize the variance of each class. Okay, so here, if you look at W transpose sigma W, it's not a vector anymore. It's a matrix. A matrix which has many, like k minus 1 different vectors. So basically, we are projecting the data in k minus 1 different directions. So in fact, if I want to know what the variance is going to be after this projection, the variance is going to be the variance of first direction of projection plus the variance of second direction of variation plus the variance of k minus 1 direction of variation, right? Because it's not just one direction, I have in k minus 1 dimensional space. So variation of the data is variation in all of these directions. So this summation, I can simply write it as trace of W sigma double. Okay. So in multi-class problem, instead of minimizing W transpose SWW, I need to minimize trace of W transpose sigma, or let me call it SB W. That was SB or SW? That was SW. Okay. With the same token and the same way of argument, you can show that you need to maximize trace of W transpose SB W. And then your objective function in multi-class case would be maximizing the trace of W transpose SB W divided by the trace of W transpose SWW. And everything is going to be the same. You can write the Lagrangian, which is trace of W transpose SB W minus lambda trace of W transpose SB W. Here, this Lagrangian is not just a scalar, it's a matrix, a diagonal matrix with some scalars in it. Then you take derivative, you set it to 0, everything will be exactly the same. Exactly the same. And the final solution would be the solution that we had here, that SW inverse SB is equal to lambda W. When lambda is a diagonal matrix, lambda 1, lambda 2, lambda k minus 1. Okay? So in multi-class problem, still the solution is eigenvector of SW inverse SW. But in two-class problem, SB was rank 1, so SB times SW inverse was rank 1. So in the solution, we had only one eigenvector. Now we have k minus 1 eigenvectors. So in k-class problem, you can project your data in k minus 1 direction, different direction. Yes?
Is there W after the SB?
Sorry?
Is there W after the SB? SW inverse SB?
Yes, sir. Yes, thank you. Yeah, and this W is matrix. So basically, each vector of this matrix, is an eigenvector of this, corresponding to one eigenvalue. Okay, any question? Yes?
How can we calculate SB for multi-class?
Oh yeah, that's a good question. How we can calculate SB for multi-class problem? SB for two class was sort of trivial. We had only two classes, and we wanted these two classes to be far apart. So it was quite clear. For multi-class, basically we want the distance between any two classes be far, right? So basically, we have to take all of these pairs, right? Which is going to be difficult, actually, to compute. Like you have to take mu0 and mu1 and mu0 and mu2 and mu0 and mu3 and then mu1 and mu2 and mu1 and mu3, and all of the combination of them, because you want all of them to be far apart. It's hard to compute this way, but there is a simple trick, actually, that you can get around this. In multi-class problem, SW is easy to compute, right? Because SW is going to be W0 plus W1, and so on. So it's summation of all of these, sigmas. Summation of all of these sigmas would be SW. But SB, as I said, it's sort of hard to compute. So the trick is that the total variance of data is the between class variance plus within class variance. You know, if I look at the total variation of the data, I can decompose this variation in two forms. Either the variation within each class or variation between classes, right? So the total variation of the data is variation between classes and variation within classes. This one is easy to compute. This is also easy to compute. You can compute the total variation of the data easily. So basically, you can compute SB as ST minus SW. SW is easy. ST is also easy. It's just sigma xi minus mu of total. I mean, all of the data points together, regardless of the class. Xi minus mu transpose 1 over n. Okay? So this is total variance. You have within class variance, so it's easy to compute between class variance for multi-class problem. Good question. Any other question? So if you don't have any other question, I'm going to start a new topic. So logistic regression is one type of classifier that we are going to learn today. Logistic regression is classifier which is pretty popular in some communities, especially between biostatisticians and people who are doing bioinformatics as well. The traditional people in that area still use logistic regression. If you have a paper in biostatistics and you can classify your data with support vector machine or something even more advanced than support vector machine, in terms of getting acceptance, it's better to use logistic regression, even if the performance is not as good as support vector machine. So it's pretty popular in some communities still. So if you recall, we start for classification, we started from base classifier, the concept of base classifier. So, and we said that in base classifier, basically, we have to compute the posterior. And the posterior was basically class conditional and some prior and divide by marginal. And then we learned about the linear discriminant analysis. In linear discriminant analysis, we modeled this class conditional as Gaussian, multivariate Gaussian. And we modeled this as Bernoulli, right? And the same for QDA, quadratic discriminant analysis, just different simplification assumption in LDA and QDA. So the idea of logistic regression is that, okay, wait a minute, end of the day, I need this posterior. why should I go through making assumption about class conditional, about prior, and then compute posterior? If I want to make some sort of assumption about the data, let's directly make assumption about posterior and model posterior without modeling class conditional and prior first. Okay? So here actually we assume that this is Gaussian, and we then learn the parameters of Gaussian. Let's make an assumption for posterior directly. Assume that this has a noun form, and learn the parameters of this noun form directly without going through the difficulty of, because if I can model this, I even don't know, I don't need to know what the class conditional was, what the marginal was, what the prior was. I don't care. Okay, that's basically the idea. So I need to model the posterior, okay, directly. The way that logistic regression models posterior is through logistic function. Okay, basically, I can, assume for the moment, assume that we have two class problems. So I assume that only two class. So y is either 0 or 1. I have only these two classes. So if y is 1, I model this by this logistic function. And if y is 0, basically y is 0 is the complement of y equal to 1, right? It's going to be 1 minus this, which is basically 1 over 1 plus e to the power of beta transpose x. In general, if I have this function, what's the form of this function? If a is 0, this is 1 and this is 2. At a equal to 0, this is 1/2. If a goes to infinity, if a goes to negative infinity, what's the value of this function? 0, right? If it goes to infinity, plus infinity, what would be the limit? It's going to be 1, right? So the form of this function is like this. When this is a, here is 1/2, this is 1, and this is 0, okay? And 1 minus this function would be 1 plus e to the power of alpha is just complement of this function. So whenever it's 0, that would be 1. When it is 1, it's going to be 0. So it has this form. Okay, what we have done here actually is to assume that we can have a linear function over x, my input. I apply linear function over x. Then I put this logistic function on the top of this linear function. Because linear function, if I say beta transpose x plus beta null, if I apply this linear function to any data point, right? It could have any values. I don't have any control. It could be anything. But so I cannot interpret this as the posterior. To be able to interpret this as posterior, I'm going to put a logistic function on the top of this, which limit this between 1 and 0. Then I can interpret this as a probability. Basically, so far, that's exactly what we have done here. I said, okay, let's assume that our probability in class 1 can be written this way, and the probability in the other class has this form. So it's a linear function which has been limited between 0 and 1 using a logistic function. Okay? In order to be able to interpret it as probability. And just be careful, here when I say beta transpose x, I didn't write this beta null. It's supposed to be a linear function, so I need a beta null. This is a general trick that I think you're familiar with. This is d by 1, and this is 1 by d, and this is a scalar 1 by 1. So I can expand x, right? Put a 1 at the end of x, and expand this beta. I can define a new beta, which is basically beta and beta null. And then my x it's beta and beta null, and my x would be x and 1. So basically here, this beta is d plus 1, and this x is d plus 1 times 1. Or we augmented our input by adding a 1 at the end to take care of this beta null. Okay. Okay, so I decided to show the probability in class 1 with this form, probability of class 0 with this form. Now I need to basically write it in terms of a density function. So I would like to have a density function for yi given xi. So the density function, I'm sure you have seen this in many cases. This simple trick that I can combine these two. I can write it this way, see if y is 1, this part is 0, and I can compute the density only using this term. If y is 0, this is going to be 1, and I have basically the density only using this part. You have seen this everywhere, like even in, no? I haven't seen that. Okay. Is it clear what we have done? We just merged these two. So I can say that this is my density function now. Okay? So this is my density function, which take care of both value of 0 and 1 for y. So y equal to 0, y equal to 1. I can represent it using this function. But the problem is that I don't know beta. I don't know the parameter of this density function. So x is given. So you give me data, you give me data points, xi and yi. You give me n of these. And I want to model it using this density function, but I don't know the parameters. We had similar problem in the past, but you knew the solution, so it sounds trivial to you. when we did LDA, we had data point. And I knew that some points are in class 1 and some points are in class 2 because I knew the label. I assumed each class, the form of each class, the density of each class is Gaussian. Then we computed the mean of that Gaussian. How did we compute the mean of a Gaussian? So if I have some points here, what would be the mean if this is Gaussian? Sorry? I can't hear. Yeah, I assume I'm talking about all of the points in this class has label 1. So how can I compute the mean of these points? It's average of those days, right? So it's going to be 1 over n1 of all xi would be the mean. So I estimate the parameter of my Gaussian this way. Why this is correct? Why this? Yes. That's basically maximum likelihood estimation of the parameter. Okay. So this is average because this is maximum likelihood. If you're not frequentist, if you're Bayesian, that's not the mean. You have to have the prior over your mean, and you have to, calculate another formula to make. So we calculated this because we somehow assume that we are frequentists, and the form of the distribution is known, the parameter is unknown, and we can do maximum likelihood and calculate the maximum likelihood estimation. So we can calculate maximum likelihood for any distribution, including this one. We can, using the data, we can maximize the likelihood and compute the beta for this one. So if you are not familiar with maximum, how many of you have seen maximum likelihood before? Okay, so very quickly, what maximum likelihood means. Given IID data, if the form of the density F is known, but parameters theta are unknown, you can estimate theta using maximum likelihood. So maximum likelihood is very easy. I can say, okay, the probability of, this is my data. This is likelihood. You remember that was likelihood. So this is likelihood. Means that what's the chance of observing this data given this parameter? Okay? Because say it's Gaussian. Given that the mean is 2, what's the chance that I see this data? Given the chance that the mean is 3, what's the chance of observing this data? So in maximum likelihood, we would like to maximize or find the theta which maximize this probability. Okay? Maximize this probability. That's maximum likelihood. So we assume that the data is IID, so they're independent. So I can write it as probability of x1 given theta times probability of x2 given theta times probability of xn given theta. Actually, true Bayesian, true frequentists are going to complain here that I wrote it this way as condition. You know, usually frequentists write it this way because you can't condition on the parameter. It's just parameter. It's not a random variable. But Bayesian think everything in the world is random variable. So theta is random variable. You can write it as a condition. But so I can write it this way. So basically, it is the product of pxi given theta. I have to maximize this and find the theta which maximizes this. Usually, it's easier to work with the log of this likelihood instead of the likelihood. So usually, we use log of the likelihood, and we maximize that, and so we show them. Usually we show likelihood by this capital L, and we show log likelihood by this L. So it's going to be log of this. Log of product would be sum of log, right? So I can write this as a cost function, maximize it, and find theta. So this is maximum likely estimation of the parameter. Okay? And if you, as an exercise, I suggest you do that. Write a Gaussian, write maximum likelihood for the Gaussian, for the mean. You calculate that, and you can see that it's going to be the average of all points. Okay? So we can use maximum likelihood here. Basically, if I want to use maximum likelihood to find the parameters because data is given, so I can find the log likelihood of this, and the log likelihood would be summation of all points over the log of this density. So the log of this density would be yi log of e to the power of beta transpose xi, which is just beta transpose xi minus log of denominator minus log of 1 plus beta transpose xi. That's for this term. Plus the log of this term. Okay? So plus log of this term would be 1 minus yi log of 1 is 0 minus this log. So minus log of 1 plus e to the power of beta transpose xi. Okay. Hopefully we haven't made mistake. Okay, so this is log likelihood, right? So I can simplify this. It is I1 to n. I have yi beta transpose xi minus log 1 plus beta transpose xi. Sorry, this is 1 plus e to the power of beta transpose xi. Right? So minus log 1 plus e to the power of beta transpose xi plus yi log 1 plus e to the power of beta transpose x. Okay. Yes. Yeah, there's a yi here because we take like. So I have this term. Cancel this term. So it's sigma yi beta transpose xi minus log 1 plus e to the power of beta transpose xi. Okay, that's my log likelihood, and I have to maximize this. So to maximize this, I have to take derivative of this L, set it to 0. So I have to take derivative of L with respect to beta. So it's going to be sigma. Derivative of the first term with respect to beta would be, sorry? yi xi. It's yi xi or yi xi transpose. See, beta transpose xi is a scalar, right? yi times beta transpose xi is a scalar. You take derivative of a scalar with respect to a vector. Is it going to be a scalar or a vector? Derivative of a scalar with respect to a vector. It's a vector, right? Because basically what derivative means that if I perturb this vector, what's going to happen to this scalar? So if I perturb any element of this vector, if it's d-dimensional, any of these d, when I perturb, what's going to happen to my scalar? So it's a vector of d. So a derivative of a scalar with respect to a vector is a vector. Derivative of a vector with respect to a vector is a matrix. You know, I have vector of d. I take derivative with respect to another vector of d. Any element of this vector change, the whole vector will change. So there's d squared directions of change. Okay? So this is a vector. But we have to be very careful that this is transpose here or it is xi. So if you're not sure, you can look at one of these list of calculus tricks, for example, the one that is the link is on my web page. So whenever you take derivative for vectors, matrix, just consult that list, because then it's going to be messy if you don't put the transpose correctly. I think it's going to be transpose. If it's not, we're going to find out later on when we want to match the dimension of all of these vectors and matrix. It becomes clear that is it really transpose or is not. For the moment, I think it's transpose, so I would put it transpose, but we're going to see. So I have to take derivative of this log. So it's going to be negative 1 over 1 plus e to the power of beta transpose xi times derivative of this, right? And derivative of this would be 0 times e to the power of beta transpose xi. And derivative of beta transpose xi would be x. I transpose. Okay, that's the derivative of L with respect to beta. So what can I do now to find the maximum? I can set this derivative to 0 and solve for beta. So if there's closed form solution, it's easy to find beta, but unfortunately there's no closed form solution here. We can't solve for beta in closed form. So if there is no closed form for beta, I have to use one of the numerical methods. I can use gradient descent, for example. I have the gradient. I can use gradient descent to find the minimum. But I can do better than gradient descent, a faster method than gradient descent. I can use Newton method. Knowing the second gradient, I can use the Newton method. Do you remember the Newton method? In Newton method, you have a function, fx. You want to solve for fx equal to 0. And that was the solution, x minus f divided by f prime. Okay, you just had this update. And according to Newton method, it gets to. So I want to solve for this. I need the derivative of this in order to solve for this. Or I want to minimize the original function. I need the derivative and second derivative. I want to solve for this equation. According to Newton method, that's the solution. What if I want to minimize this function? If I want to minimize this function, means I have to set the derivative of this equal to 0. So derivative of this equal to 0. So I need second derivative. So that's for minimization. So I have the derivative of likelihood. I need the second derivative. Basically, I have Jacobian. I need Hessian of the likelihood. So I have to take second derivative. Okay. So to simplify the task, let me take derivative of this part first, because I need to take derivative of this and then derivative of this fraction times this, and just to make it easier, let me take derivative of this fraction first and then I apply it here. So I use this notation. So I call this fraction pxi beta, given beta, because it's in the form of, it has this form of density. I just call it pxi given data. Okay, so let me take derivative of pxi beta with respect to beta. So derivative would be derivative of e to the power of beta transpose xi, which is e to the power of beta transpose xi times derivative of beta transpose xi times denominator minus derivative of denominator, which is of xi here. Derivative of denominator times e to the power of beta transpose xi divided by denominator squared. Okay, so it is equal to e to the power of beta transpose xi times 1 plus e to the power of beta transpose xi. I just factored this e to the power of beta transpose x. So I have this term minus e to the power of beta transpose xi. So these two cancel each other. I have 1 plus e to the power of beta transpose xi squared. So it's e to the power of beta transpose xi divided by 1 plus e to the power of beta transpose xi squared. Which I can write it as 1 times 1 divided by 1 plus e to the power of, and sorry, I had xi here. So I can write it as 1 plus e to the power of beta transpose xi times e to the power of beta transpose xi divided by 1 plus e to the power of beta transpose xi. So this squared here, you know, I just break it down to 1 plus e to the power of beta transpose x. One of them is here, the other one is here, and I have 1 times this. Okay, is that okay? Clear? Sorry? Xi. So this, if you remember, I call it P. And this is the complement of this P, right? This is 1 minus P. So derivative of P with respect to beta is 1 minus P times Pxi. Now let's take the second derivative. So derivative of second derivative of likelihood. So it's going to be sigma so the first term, derivative of the first term, that's the first term, is just 0, right? With respect to beta, it's 0. Minus the derivative of this beta xi, beta times xi transpose, which would be the derivative of this fraction times xi plus the derivative of xi times this fraction. So the derivative of this fraction, we just computed. So it's minus 1 minus p xi given beta times p xi given beta. That's the derivative of the fraction time, and it has xi times xi transpose. Derivative of fraction times xi transpose plus derivative of xi transpose with respect to beta, which is 0, times this the fraction. So that's my derivative. So I think I was right that it was xi transpose, because you can see that xi times xi transpose is d by d matrix, right? Or if you augment it at the beginning, it's d by 1 times d by 1 matrix. And the second derivative is supposed to be a matrix, because you're taking derivative of a vector with respect to, sorry, you're taking derivative of a scalar with respect, you're taking derivative of a vector with respect to another vector. It's supposed to be a matrix. So it is a matrix, that's correct. So that's second derivative. So I have the first derivative, I have the second derivative, I can apply Newton method. So according to Newton method, I need to initialize beta, and then nu beta would be old beta minus the first derivative divided by the second derivative, or in the matrix form, the derivative of, this matrix inverse times the vector of the first derivative times the Jacobian. So basically, I have to compute I have to take the inverse of this times so I can initial beta with some values and then iterate until it converges. Okay? I can write it in a better form, if I use vector and matrix notation. Any question up to this point? Is it clear? Okay. So I'm going to define some new matrix and vectors to make this formula simple. So I define vector y to be n by 1 vector of all response variable or labels. At the beginning we had n data points and we had n labels. All labels. Okay. I define capital X as a matrix. So I have n data point in d dimension. Usually we show our data matrix as d by n, right? Dimension times the number of data point. I just use the transpose of this. In this case, I don't follow our general convention because it's going to be easier to show it as n by d. So each row is a data point. Each column is a feature. In fact, it should be d plus 1 because I assume that the data is augmented. I added 1 to each data point. So this is my x. I define vector p This is a vector. I define vector P is a vector of all of these values. So it's n by n by 1. Such that Pi is just Pxi given beta. And to be clear, we have two beta, beta new and beta old, or beta at iteration r plus 1 and eta at iteration r. So this is beta that you already know, beta at iteration r. Yes?
D plus 1.
Sorry?
X is the matrix D plus 1.
Yeah.
X equal 1.
You know, the linear function has this form, right? This is d by 1, and this is 1 by d, this is d by 1. So I can get rid of this and write it as augmented x, add 1 at the end, and make this d plus 1 as well. Okay. So this is p. I can define W as a matrix, which is n by n. It's diagonal. Such that elements of diagonal matrix means Wi is just this 1 minus pxi given beta times pxi given beta. Okay? Okay, so now I can write the first derivative using this matrix notation. So I can write derivative of L with respect to beta as, you know, I have this summation. This is basically, what was this? It was, see, it is summation of yi times, no, so yi times xi, right? We have it. Yi times xi minus this p times xi. Okay. So now I have vector yi, and this is going to be I can factor this xi, that's going to be yi minus p times x, right? So that's y minus p times x. And I think I need a transpose here. This is n by d plus 1, right? And this is n by 1, and this is n by 1. Yeah, if I take a transpose here, that's going to be 1 by d plus 1. And I can write the second derivative This is my second derivative. You know, I have a matrix W, which is diagonal matrix, and each diagonal value contains this product, 1 minus p times p. And then I have to multiply this with xi transpose, so I can write it as x w x transpose. This, or x transpose wx, because this is going to be d plus 1 by n. This is n by n, and it's n by d plus 1. Yeah, it's x transpose w. Okay, and also I have a negative sign here. Now I can say that nu beta, or beta at time r plus 1, is old beta minus first derivative divided by the second derivative, or the inverse of this times the first derivative. So I have x transpose wx inverse times the first derivative. Okay, see, it's now very easy to compute logistic regression. A data set is given to you. For the moment, we assume that this data set is two-class problem. So we want to classify this in two classes. So xi, yi is given, and I have two classes. So the only thing that I need to do is to compute this. I put all of my labels in a vector, call it y. I put all of my data points in a matrix, call it x. I can initialize beta with some beta, just randomly choose a beta, and using this random beta compute p. And using this random beta compute w. Okay, now the beta that you have chosen times this, everything is noun. It's going to give you a new beta. Using this new beta, you need to compute p and w. Okay, so this w is w computed with r, and p is computed with r as well. So you're going to iterate these until it converges, right? And then you have your beta, and when you have your beta, you can compute the posterior of class. Yes. Sorry?
What is R?
R is iterations. Let's call it T.
Oh, okay.
Whatever, It's just index of iteration. The first iteration, second iteration, third iteration, just index. Number of iterations. Any question here? If you think about this, the size of the parameter that you have to estimate here is just beta. So how many parameters do you need to compute? Just d. For d-dimensional space, you need to compute a d or d plus 1 parameters. What was the number of parameters that you used to compute in LDA? You had mean of this class, you had mean of the other class, you had the covariance matrix of this class, covariance of the other class. Mean by itself was d-dimensional, so you have two of them, 2d. Covariance was d by d plus 1 divided by 2. So you had two of them. See, the number of parameters was in that case was way more, which is bad, because when you don't have enough data, you can't rely on your estimation for the parameters. So the less parameters you have to compute is better. So that's one of the advantages here, that we have way less parameters to compute, because originally we got rid of class conditional, and prior we directly try to compute the posterior of the class. Okay, any question? Okay, see you on Thursday.